Very well. So as I was saying, we keep having people joining. That's great. So as I was saying, today we have Kevin Jones from Catalyst, and he's going to tell us all about what can be done with satellite monitoring. Kevin, the floor is yours.
Thank you, Andrea, and thanks everyone for joining today. Really appreciate it. Just by way of introduction, as Andrea mentioned, my name is Kevin Jones. I'm the Chief Product Officer here at Catalyst, and my background is in satellite remote sensing. And so I've had a long career developing products and applications for operational use and use by hopefully folks like you who are kind of wondering about how this satellite technology works and whether it's the right fit for you and so on. And that's what I hope to achieve in today's call, is to impart some of that knowledge that I've accumulated over the course of my career and help to clarify any questions you may have about its applicability specifically for rail corridor monitoring. I'll be showing a few different use cases. I'll talk a little bit about the technology itself, and also give you kind of a live demonstration of it. So I do like to keep these things interactive. So I thought I would start with a poll, and essentially I'm going to launch that right now. So just very simple question, yes or no. Do you currently use satellite imagery? And that could be any use. You've purchased satellite imagery, or you've used it through a consultant, or you're using a solution that leverages satellite imagery. I'm just trying to get an understanding as to people's familiarity with it. And there's obviously quite a lot of different satellite imagery. Just before I start sort of giving a full introduction, the availability of imagery is definitely on the rise. That's been mainly as a result of if you follow kind of some of the work that's being done with SpaceX, which is quite an innovative company out of the US. They've really changed the game in terms of making space more accessible by having the cost to launch satellites reduced drastically over the last very few years. And so what that's resulted in is quite a few companies have launched satellites that are able to observe the Earth. There's different configurations, and that imagery can be leveraged to develop operational data layers, which is what we're going to be talking about. So I'm going to end the poll there, and think I can share the results. I'll just do that now. Oh, we've got a comment about.
Kevin, we have two people asking if Google Maps count.
Sure. Yeah, Google Maps counts. I mean, the imagery that's visible within Google Maps is sometimes it's aerial imagery. It's captured by planes, especially over in urban areas. But as you kind of leave the urban areas, a lot of that data is collected by satellites. I guess the key differentiator with Google Maps is that you're looking at a static image that may or may not have been collected recently in that case, whereas what we're talking about here is a more bespoke monitoring approach where you're actually tasking a satellite or leveraging satellite image archives to build an application layer. So the subtle difference there, but yes, absolutely. Google Maps does make use of satellite imagery. So I'm going to share my screen and start the presentation. I've got quite a lot to get through here. And we do have the full hour, right, Andrea? That's
yes, that is correct.
Okay. Hopefully everyone sees my screen. That's should be up on the left.
Yes,
yep.
We can see it perfectly well.
Awesome. Yeah, so topic today is leveraging satellite-based monitoring for rail corridor risk identification. And I will go through a couple of different scenarios. But just before I do that, I'll quickly explain a little bit about who we are as a company. So Catalyst is a member of TRACCS, and we have been developing satellite Earth observation technology for a number of years. The company was actually established in 1982, so we're in our fourth decade of operation. We are based in Canada. We have offices in the Ottawa area, which is where I'm located today. We also have offices in Toronto. And really sort of if you look at what it is that we have been doing and what we do today, it's kind of nicely summarized on this slide. So PCI Geomatics Catalyst it's a brand essentially that we have developed, but fundamentally we have developed software solutions to enable companies to use satellite imagery, correct that satellite imagery, and then perform analytics to extract information from that imagery. If you look on the left-hand side of this chart, we have been doing that for, like I said, many decades, and there are hundreds and thousands of clients around the world who use our software every day, who I would characterize as kind of similar to my skill set, which is remote sensing experts. So they're able to use satellite imagery, bring it into our software, transform it into information layers, and then provide that. But in this case today, what we're talking about is the fact that Catalyst or PCI, we have developed a data as a service information product, which we call Catalyst Insights. And what that is essentially us using our algorithms to combine that with satellite imagery to solve a particular problem over an area of interest. And so today we'll be talking about a couple of different risks related to rail corridors. We'll talk about ground displacement, which can be monitored using satellite remote sensing or Earth observation. And also we'll be talking about vegetation management or vegetation encroachment in and around that kind of infrastructure. So just some other information about us. I'm not going to spend too much time on this one, but we have developed a extensive set of algorithms. So if you are interested to speak with us at some point, what you'll find is that we do have the ability to address kind of multiple potential problems. So if you're curious about Earth observation and what is possible, what isn't possible, you're going to have a broad discussion about kind of the different satellites, the different resolution, the different repeat frequency, and whether the information that can be extracted is suitable for your application or not. Because we've been working in this industry, have developed technology for multiple types of applications, we can actually have a kind of a broad discussion with you about that, and we're happy to do that. But really what we like to do is address kind of those diverse problems that you may be having with your business, where Earth observation can play a role. We like to pick the right sensor, because as you'll find out, if you dig into the world of satellite Earth observation, it gets a little bit overwhelming. There's resolution and spectral bands and how frequent the imagery is collected. There's quite a few things to take into consideration. And then so choosing the right data for your application it can be a little bit complicated. We sort of simplify that because of our experience and our knowledge with the industry. So we're able to recommend some solutions, and then everything that we do is going to be cloud-based over an area of interest. So you'll see kind of what our platform looks like in a few minutes. But essentially, that's what we try to do, is to deploy this so that it's a dashboard-like solution that gives you visibility into what risks may or may not be present within your infrastructure. So the first thing that I will brief here is something that we like to talk or refer to as vegetation management. And this could be a risk in and around your rail infrastructure. Obviously, you've got typically a lot of rail infrastructure that's passing through urban areas, but then you also have some rural areas where you've got like large expansive sets of the network, which is surrounded by vegetation. So pruning that vegetation, understanding where it's located, and how it should be better managed is a key concern. This is a common issue that's kind of referred to as vegetation management. And so, there's two possible ways of addressing this problem. The traditional way, which is what we see on the left here, is what we would call the cadence-based monitoring. And this is typical for rail, but also for hydroelectric utility companies, where you have field inspections that are happening along certain sections of the network on a regular interval. So, today we're doing this stretch, tomorrow we're doing that stretch. And then at some point, you manage to inspect every single span along the network, and you're able to characterize the risk along that network. And that's a fine approach. One of the limitations of this approach is that you may not be keeping up with the rate of vegetation growth that's happening in other parts of the network, especially if it's taking you multiple years to cover the entire network. So really what condition-based monitoring is how it differs from cadence-based is what you could do is you could do that large area scan with satellite imagery. We apply a technique which is called 3D reconstruction, where we collect imagery in stereo configuration, and then we build up a elevation model over very, very large areas, and we're able to identify the heights of the trees. And then what we can do is map the risk of either fall in or grow in, and also map the proximity of the vegetation relative to the rail infrastructure. Furthermore, what we can do is identify the health of that vegetation over time. As you'll see, hopefully through this talk, the availability of historical satellite imagery is definitely there on a global basis. So today, it's kind of an incredible time for this technology. You can point pretty much to anywhere on Earth and have access to imagery that dates back, at a minimum 10 years for medium to high resolution, and then even 40 years if you're looking at lower resolution satellite imagery. The data is just available. It's all cloud-based, and we're able to access that data and derive historical analysis over the entire network using that imagery and our analytics. So really, the condition-based monitoring allows you to look at the historical, like what are some problem areas that have occurred in the past, and then on an ongoing basis, because the satellites are collecting imagery on an ongoing basis, we can refresh and map the vegetation at a particular set cadence. It will depend on the area of interest and how big the risk is, but typically we can do as close as every month, if you will, or even closer than that. But for vegetation, obviously, the cadence, more logical cadence would be like every 6 months or every year, something like that. So really what you're able to do is to shorten the cycle and get back to the entire network on a more regular basis, and then triage and identify higher areas of risk for visual inspection. So this gives you a better assessment, hopefully should reduce cost, and more importantly, reduce the risk of anything happening within areas that are of high risk. So Earth observation and the role of Earth observation within that is satellite imagery. As I mentioned, you can task the satellite. You can, there's other technology that is available, like UAVs, which are very good, but they're limited in terms of what area they can cover, because you have to send a crew in the field, and you're limited to how much of an area you can cover. Airborne LiDAR is excellent for mapping the network and mapping infrastructure. But again, the cost and the complexity of collecting that data on a regular interval is different from using satellite-based Earth observation. So these are some of the key points. The way that this kind of works in reality is displayed here. So we have satellite imagery that is collected. Either there's historical imagery that's available in the archives, or you have a set collection of specific satellite imagery over your area of interest at the right resolution, at the right repeat frequency. And then we need to have a detailed map, so we can map it ourselves, or we can leverage the information that you have of your network. In this case, I'm talking about the actual rail infrastructure, like where it's located, and that needs to be provided to us in a geospatial data format, like vectorized data format. And then we can overlay other data which may be interesting, and I'll show examples of that, like historical landslide locations or burn perimeter for wildfires in Canada. You obviously would know that there's quite a few active fires within Canada at the moment, and so understanding where those burn fire scars are located and layering in the elevation data on top of that can be useful to assess the landslide risk post-fire, where you've got less vegetation kind of holding that slope in place. Potentially there's more risk for slope failure in that particular area. So you can layer all of this information in. We do the processing, which is what you see in the middle. We'll do things like extract the tree heights, we'll map the vegetation, we'll apply a model which you can help us to define, but typically what we would do is map the heights of the trees, proximity to the infrastructure, and then assign a score in terms of the risk. Could be low risk, medium risk, or high risk, and classify that so that you can see it on a map. And furthermore, you could consume that data into your own geospatial application yourselves. So a second area of risk that we can provide help with is what we call ground displacement. And this obviously can be of concern in and around rail corridors where you're adjacent to steep slopes or slopes that are prone to rockfall or erosion. And so in this case, what we use is a different technique, which is called INSAR. It's short for interferometric synthetic aperture radar. But the way that INSAR works, just really, really briefly, is you have if you think of a radar gun, like a police officer that's collecting information or trying to give you a speeding ticket, they're using a radar instrument. Think of this same instrument flying in space, and the way that we can use that is we can take an image on one day, measure the ground, and then we take an image on the next day or 12 days later or whatever the frequency is, and then if there's any disturbance on the ground, which is like exaggerated on this figure, but what you can see is the ground is moving in what we call the line of sight, or it's moving away from the sensor at quite a fine scale, like only a few millimeters. So that feature will return a signal back to the satellite, which we can quantify and understand the ground movement that is associated with that delay in that signal. And where that becomes interesting is kind of on this illustration, which is you can collect this data on a frequent basis over a long time series and build a time series analysis, which is what you see this graph in the middle of the illustration here, where you've got everything is mostly stable along a long period of time. So I'm just kind of highlighting that as kind of the stable period. And then at some point, there's an acceleration event, or there's something that happens that causes displacement to accelerate. We would not be able to tell you that. We're not geotechnical experts. But what we can tell you is that in the satellite imagery, we can identify geospatially correlated areas of displacement that you've got multiple points. Each one of these points is what we call a pixel in the imagery, and that all of these points are kind of exhibiting similar behavior. And so where that becomes interesting is to identify potential what we call precursory displacement. So oftentimes you've got signs of a rockfall or signs of a landslide failure occurring before the actual catastrophic event happens. And so that could be potentially integrated into an operational scenario to protect people and equipment, to do closer inspection on a particular area of interest, to better characterize that risk. So the question that we often get asked with this technology is the accuracy, and I think for the vegetation it'll be the same thing. We often get questions about accuracy, and one of the key things that I would say is that satellite-based Earth observation is not meant to replace in situ monitoring. It's really meant to complement it. So, you know, the ability to map large areas on a regular basis without having people go to the field with survey instruments is really where this technology shines. It may help you to uncover blind spots, maybe some slopes that you thought were stable or that you've never surveyed, you know, are showing or exhibiting some characteristic of displacement. And so you might take an action to go and inspect that slope more closely, send geotechnical engineers to sort of deem it safe, that kind of thing would be how satellite Earth observation really helps. Having said that, ourselves and, you know, in the body of literature, you will find that both for vegetation management and for INSAR, people have done the work to assess the precision. And this is just an illustration of a GNSS or a GPS station that collects X, Y, and Z information over a particular location in California. There's lots of these. You could do this dedicated surveying comparison. And we see strong alignment or strong agreement in not only the delta between the in situ instrument and the satellite, but also the sort of the trend. You know, there's an initial decrease and then a stabilization, an increase and a decrease. So the temporal trend and the RMS E value in this case is close. And there's a significant amount of literature out there that is, you know, I think at this point, giving end users like yourselves confidence that the validation and the precision of this type of technique is definitely there. Having said that, not meant to replace in situ technology, really meant to complement it, identify hotspots, and hopefully reduce cost and risk in so doing. So the next thing that I want to talk about is our platform, or like what it is that we would deliver. So in the case of what we do is really the deliverables for vegetation management. So here what we would do is provide a vegetation classification. So we tell you where the vegetation is located along the corridor. We tell you the heights of the trees. And furthermore, we give you the proximity threat analysis. So we would score it, you know, no threat, medium threat, high threat, depending on the proximity. And that proximity can be, like, we can set those proximity levels, or we can work with you to determine what those thresholds are. Furthermore, we can assess the risk to fall in or grow in. So is this vegetation, if it were to fall, would it fall on top of the actual asset itself or the surrounding assets, or is it you know, is it safe if it still falls? Another data layer that we can provide is the vegetation health analysis. So we can do long time series trend analysis to identify the health of the vegetation over time, and then assign a score to the risk based on whether it's like healthy vegetation or unhealthy vegetation. There's certain signals that tree canopy can be detected from satellite imagery that we can map and quantify, and then use that as a proxy to identify risk. And then the way that we deliver the data is typically through a platform, which I'll show in a minute. I'll give you a live demonstration of the platform. But also we can deliver the data in standard format. So it can be ASCII text files, it can be, you know, Excel data, it can be geospatial vector formats like shapefile or geodatabase or what have you. And then that information can be integrated into your platform if you're using geospatial technology like QGIS or Esri or any of those. We're absolutely compatible with all of those. The sort of the second thing which I talked about, which is ground displacement monitoring. What we would deliver in this case is what is termed cumulative ground displacement. So we'll give you point data. So this is vector data, geospatial data, and every point has a measurement over time that tells you how much the ground is moving relative to the origin at that time. And so what this then allows you to do is to assess the risk of slope failure or slope movement, slope creep, in the case of a slope or any kind of ground movement. You can assess that. You can kind of draw polygons and get information interactively on our Insights dashboard. The other thing that you get is velocity. So because we're measuring the displacement every time a satellite image is collected, we can join those displacement measurements and calculate velocity. And where that becomes interesting is where you have acceleration in the displacement, that's going to be visible in the velocity. And that's really kind of can be used as a warning sign for precursory displacement before land displacement occurs. So that's where it kind of becomes interesting. The other thing that we can do is integrate in situ data. So we can use ground instrumentation. You saw that graph that I showed earlier where we had the in situ GPS 3D ground station data together with the satellite INSAR data. So we can combine those two together so you can draw polygons, you can understand the risk relative to something you're seeing in the satellite derived analytics, and then compare that to any ground data that you have. And that may help you to correlate and bring more confidence that you are seeing something in the satellite imagery that you have quantified and measured with your in situ instrumentation. Or it might help you to complement some information. Maybe your in situ instrument is pointing at the feature kind of in a particular way that you're not seeing from the satellite, so you can kind of get multiple views of the displacement and can characterize it more closely. Just to give you kind of a feel for what the reports look like. So this is a screenshot of our dashboard. I'm going to go to that next. But this shows you essentially all of the network has been mapped out. Along that network, you've got all the vegetation that's been mapped out, and then you've got individual threats that have been identified along that network. And those threats are spatially visible, so you can, where you see the red X's, you can zoom in on those, and you can understand exactly what the risk is. But also they're visible in a tabular format. So if you wanted to identify the highest threat, you could sort this table, you could click on the highest threat, and then zoom straight to that feature on the ground. Here's kind of a zoomed in version of the vegetation assessment. This is a utility corridor, but it could be the exact same information along a rail corridor where you have a span which has been flagged as being red or higher risk. And the reason it's been flagged as higher risk is you can see this green polygon. We have mapped not only the location of the trees, but also the height of the trees. And furthermore, we have understood what is the height of that tree and its proximity to the infrastructure in this case. So we assign a threat level or a risk level based on that, and then that can be useful for understanding the risk. This is an example here that's specific to rail corridor infrastructure. So what we have here is a piece of rail corridor you can see along here. This is on the southern part of the United Kingdom. It happens to be near Dover, Pas-de-Calais, where the Euro channel is, and there's historically been some risks associated with landslides and rock falls in and around this particular stretch of rail corridor. And so in this instance, the operator is interested to quantify that risk. And so what this is essentially showing is I've selected a number of points that are flashing red, and those points are then displayed in this chart. You can see that the origin is 0, and then the displacement values is every single satellite image that is collected over time. We get a displacement measurement, and so we can see what the trend is. Now, this may be a normal linear trend, or it may not be. You can definitely see that there are some other slopes along the same ridge that are not red, that are green, essentially. So what you could do is you can sort of draw an area over this location and compare those two, and the time series graph will show you kind of like a stable area versus a linear trend. So this is really a useful tool for geotech analysis, where you can identify areas of concern and then take further action to better quantify the risk. So at this point, I'm going to switch to kind of a live demonstration. So let me just get set up for that. Everything okay so far, Andrea?
Everything great. I don't see any questions here in the chat, so we are great so far.
Yeah, go ahead.
Folks, if you have any questions that you don't want to forget, you are welcome to type them in the chat, and so we will address them at the end.
Perfect. Yeah, so this first example is actually very interesting, because like what we've done in this case is we have mapped all of the primary rail infrastructure across all of Canada in this case. And then we simply overlaid information that could be useful to triage and understand areas of risk. Obviously, this is tens of thousands of linear kilometers of rail to monitor, and so doing so, with surveying or visual inspection for vegetation and landslide can be quite onerous. So really what this allows you to do is to understand the target areas, and I'll just kind of turn some of these layers on and off so you can get a sense for them. But this is the rail infrastructure, number one. And then furthermore, what we have is here we have water occurrence. So this is like where there has been flooding that has occurred in the past. So this is temporary water, which is what we're showing here, as opposed to permanent water like lakes and rivers and things like that. So we can, from satellite imagery, using multiple decades of data, we have derived temporary surface water, so an indication of where flooding has occurred. That's what that layer is. Furthermore, we have access to landslide data. So this is historical landslide data that has been reported. That's what this is showing. Using satellite imagery as well, we can identify historical wildfire burn perimeters. So you can obviously see there's quite a very, very large areas within proximity to the network that have been subject to wildfires. Most notably, people will remember Kelowna, Kamloops within the last few years. There's been quite a few wildfires in that area, and those are close to populated areas and close to rail corridors. And obviously, as a result of that wildfire and the burn scar, you have an exposed slope, which is more prone to landslides, which have occurred recently in that part of the world. So really, by combining all of these layers together, what you can sort of get a sense for is there are obviously higher risk areas along the network where we can do analysis and get more detailed information on where the risk is. And the kind of the zooming in from that, one of the things that was interesting for us when we did this analysis was Lions Bay, which is this is a community on the Sea to Sky Highway between Vancouver and Whistler. And this community did suffer a catastrophic landslide in December of 2024, so only about 6 months ago. This is the location of the landslide. You can see as I hover my mouse here, this is the mudslide that occurred on December 14th. And what I have displayed here is the railway network. So you can see that's the Canada-wide railway network, and that particular stretch of railway along the Sea to Sky Highway. So in this case, the debris, the mudslide was limited to the highway, which is the Sea to Sky Highway, which was closed. But obviously you've got the rail infrastructure that's adjacent to that. And so what's interesting is what we can do is we can measure the ground displacement. So that's the layer that I've just turned on there. And one of the things that popped out to us is this sort of grouping of points here, and I'm going to select them. And this is just to kind of show you the interactive nature of the tool. So I've just selected those points. And what you get is a time series trend. So you can see as I move my mouse, it tells you the date of the acquisition. So we did our analysis starting in the spring of 2024, and then through till the end. So this was right the day of the incident, or a couple of days before the incident. And what starts to happen is you are able to get signals that show acceleration, and you'll note kind of a linear stable trend, and then all of a sudden there's kind of a drop or an acceleration. You can see that when you look at the velocity as well. So you can see kind of that accelerating velocity trend that's visible right around August timeframe, and then in December there is the landslide. So this may not pinpoint exactly the location of the valley where the landslide occurred, but what it's telling us is that there is displacement occurring in and around the network. And so what that can do is it can help you to assess risk. And so what we do in this case, I'll just turn off the INSAR data for a second, and we can update the risk information dynamically as satellite imagery is collected and identify the risk to the network. So you can see in this case, we've identified a higher risk to the rail segment because it is within proximity to the displacement that's occurring upstream or up this particular valley. So that's kind of a zoom out at the national scale. So again, because imagery is collected nationally or globally, you're able to do this kind of analysis over large areas, but also zoom into specific locations. Another example, which I was showing in the slide deck, is a rail corridor over Dover. So this is the southern part of the UK. This is what I was showing earlier. And so what I can do is I can select an area of interest. This is the area that I was kind of showing in the illustration. So I can select those points again, and I can get a time series chart that shows me the displacement of that particular area. You can see it there again. And I can draw another area that's adjacent, that's also on the slope. And then you can kind of see the contrast, right? So you can see kind of like the stable area, which is over here on the left, versus this kind of exposed slope, which is showing a different pattern. So that kind of, is useful information as to how the land is moving in and around the critical infrastructure. So that allows you to do this kind of analysis. We have other tools where you can compare over time, and you can change the time series over here to be like, the last 2 years, and for this area on the right to be kind of a different time period, and you can kind of swipe back and forth. There's quite a bit of functionality built into this tool that we do make available. Another example here, and I'm almost at the end of my examples, and I want to respect the time and make sure that people have time for questions as well. But this is another stretch of rail where we've actually combined the risk relative to trees, the risk relative to flooding, and the risk relative to displacement. And I'll just turn those layers on and off kind of one by one. I'll start with the rail infrastructure. So this is the actual rail infrastructure. This is kind of a buffer area where we performed our analysis. So we only looked at a buffer area of 250 kilometers. And one of the first layers that's kind of interesting is the flood extent. So again, using historical information derived from satellite imagery, we can identify the past flood events and where those are relative to the actual infrastructure. So you can see that particular area there is prone to flooding in the past, and we can highlight that on the map. We can also highlight the displacement. So this is the same kind of information as I showed on the steep slopes. And we have some information along the actual rail infrastructure itself. We also get some signal in the sort of the neighboring areas like these towns or some of these open areas where you have some other infrastructure as well. But in our case here, what we're kind of mostly interested in is the rail infrastructure itself and the risk relative to those spans of railway due to trees or ground displacement or flooding. And sort of the last layer, which I'll show there, is the risk related to trees. And you'll see when I zoom in, you have what we've done is we've mapped specific trees that are posing a higher risk. You can see there the height of that tree is 6.2, I believe it's meters, and its distance, it's 8 meters away. So we can apply a buffer and say if that tree is 8 meters or less, or we can make it 7 meters or less, 6 meters or less, 5 meters or less, and then classify it based on that. Similar here, this is a vegetation assessment, kind of more specific, but this was the example that I showed in the live demo where we have the individual segments within the network that have been mapped to identify the risk relative to vegetation in this case. And I'll just kind of keep zooming in. This is one of the areas that was in the slide chart. And what's kind of nice about this is you can understand the risk relative to, so if I turn off the power lines and the vegetation outlines and so on, and just be left with the tree threats, I can sort that. So you can see here I've sorted by the highest threat due to a tree, and I can just instantly kind of zoom in on that tree. So if I double click here, the map will bring me to that specific location where that tree has the highest risk. Yeah, so there's that specific location, and I can sort of turn all those layers back on and sort of complete my analysis. But just to sum up and open up to questions, I'll just flip back to the deck real quick. The data, as I showed, is geospatial data. It could be provided that way. We also provide the information in kind of a tabular format, but yeah, that's the main content, Andrea, that I had. I had one sort of last poll, I guess, which is, now that you've seen this, maybe it jogged your memory and you heard some conversations with colleagues about, oh yeah, now I know what satellite imagery is. It's ringing a bell. I guess my question to you would be, at the end of all this, what is your main hesitation from a business point of view? Is it the cost? Like, if you understand what the cost is it the technical fit? Meaning you don't maybe understand the accuracy, or you have hesitations around the accuracy or how you would use it, or maybe it's just lack of awareness. Like, you've never heard of this, or maybe you've heard of it, but you haven't sort of looked into it in more detail. So I'll leave that open for a couple more minutes, Andrea, and I'll pass it back to you for.
Definitely, yes. Let's give people a moment to gather their thoughts and then answer your poll. I want to say, Kevin, this was a really thorough outline of everything that can be done to mitigate risk and to make our jobs a lot easier. So Martin is saying thank you for the presentation here in the chat. I have a question posed by someone who had to leave, and then you can perhaps address. I think George has a question as well. So someone here, Franklin, asked, do you have experience quantifying the state of rail lines With millimeter accuracy, you may be able to catch buckling or other pre-failure indicators.
So the actual rail infrastructure itself, I would say that is not something that is typically done with satellite imagery. I would think a more appropriate technology there would be the actual cameras that are mounted on the trail, on the trains, to like image the rail infrastructure and identify weaknesses along rail ties and so on. That's really kind of at a different scale in terms of the resolution. I would recommend more the use of that kind of technology. Really what we're talking about here is some of the risks that may not be visible because those cameras are pointing at the rail ties and the rail infrastructure itself, but they're not looking outside at the slopes. They're not looking at the trees. Like, that is really where this technology shines, is to identify some of those areas of risk ahead of time to take a further action, whether that's trimming vegetation or better quantifying the risk.
Yeah, that's a great point, Kevin. Thank you. We have someone else asking if you have any experience in India, and if not, what are the challenges of adopting this for Indian conditions? I don't know if you'll be able to answer this, Kevin.
So we are a global business. We've been doing business around the world for decades. So absolutely, we have experience in India. We have customers in India. One of the lead remote sensing organizations in India is our customer. We do have experience working in that part of the world for sure. In terms of the particularity of working in India as it relates to rail infrastructure, I think it would be similar in terms of like the common issues that we encounter is the availability and completeness of the network itself, like the data that tells us like this is where the rail infrastructure is, these are the spans, these are all the key assets. Like the basic mapping of the infrastructure enriches our analysis, because if we're able to layer our risk information on top of the asset information, the better that asset information is, the better the risk analysis would be. So I would suspect that in India, you would have issues around the quality and availability of that data, just like other parts of the world. Some parts are better than others. The other consideration I would potentially see is the availability of satellite optical imagery. For those of you who may know, these satellites are essentially cameras in space, and they're pointing down to the ground. And so they can take an image under the following circumstances. The sun is illuminating the ground and it's reflecting its rays. So that surface reflectance can be measured by the satellite. And there's no clouds and there's nothing obstructing the visibility of the ground. And in India, just like in other tropical parts of the world, you do have a lot more clouds, so it can be more difficult to get imagery. But the good news is there's a lot of satellites that are collecting imagery. There's a lot of opportunities to collect imagery. And typically you can open up a kind of a collection window and get information to be able to complete the analysis.
Thank you very much for that. Giorgio, you had a question. You raised your hand. Do you want to pose it? Please unmute yourself and go ahead.
Do you have a urban rail application for this technology?
I'm sorry, George, your voice is a little bit low. Could you repeat?
Do you have an urban rail application for this technology?
Yeah, absolutely. So the satellites are orbiting around the Earth, and they're able to collect data anywhere. So in urban areas, we can absolutely collect imagery. What I would say in that case is typically what you'd want to do is you'd want to collect higher resolution data in urban areas, because you'll have a lot of obstructions, you'll have buildings, you'll have vegetation, you'll have things that are obstructing your view of the actual rail infrastructure and the surrounding areas. So as I mentioned at the beginning of this presentation, there are quite a few different satellites collecting imagery at different resolutions. So you can get down, one of the slides that I had there, you can get down to 1 meter or even higher than 1 meter resolution. And that's one main consideration that I would apply in the case of urban areas. Another thing that is important is the sort of the characterization of the displacement due to the buildings. And so we do have technology that's able to identify the displacement that is attached to buildings in urban areas, and we can separate that from the displacement that's happening on the ground. That's another key consideration, George.
How about train tracking?
Yeah, so the train tracks themselves, like I showed. So if I'll just kind of pull this up again here. You can see here the actual train track itself, right? And then you have a point or a displacement point that is visible on the train track. Now, in this case, this imagery is kind of lower resolution. It's roughly, there's a point every 20 meters, but you can collect higher resolution data and have higher density data along the actual train tracks themselves.
No, I was thinking more of the actual train or transit unit.
Oh, I see. So whether the what would you be looking to do there, George? Like to
Well, one of the things that customers want now is on-time arrivals. So if you know where your train is, you know whether you're going to be on time or not. Or if there's something happens down the rail, you can start mitigation procedures. So
Yeah.
would this technology be appropriate for that?
It could be. I would sort of lean more towards things like GPS and things like that for navigational purpose, for monitoring where your assets are. I'm sure that's like across the fleet. That's very common. But if you're maybe another way to answer your question, I think I saw a question pop up on the chat about the frequency, the cadence, because that's often, it's related to what you're asking about, George. So the satellites are orbiting every 90 minutes. They complete an orbit, and the Earth is rotating underneath. And one satellite orbiting around the Earth has what's called a revisit cycle. And so to come back to the exact same place on Earth to monitor the train or to monitor the train station or whatever it is, that can take upwards of like 12 days or multiple days. So like what you're describing with a single satellite, not really suitable, because like in 12 days, a lot happens and you're probably looking for more like every minute kind of thing. There are constellations of satellites that are launched now. So the revisit is more like every day. But if you're looking for like every minute or multiple times per minute, like this is really not the solution. It's more like GPS type solutions or that kind of thing.
Thank you.
Yep, no problem.
Thanks for your question, George. So, Kevin, I think that you were referring to Franklin's other question. How quickly can you obtain fresh imaging? I'm wondering if this can be used for quick identification of tree fall over a large area after a large storm. That's a problem we have regularly, and I believe it's going to only increase with the state of global warmth.
Yeah, no, absolutely. And you know, to kind of answer that question a little bit differently, if you were trying to characterize the damage assessment, if you will, like where have trees been affected, there's satellite imagery being collected like every day, like, basically. So your ability to either leverage existing satellite imagery that's being collected, or to task a satellite to do an assessment, like we're talking days. In some cases, we're talking hours. Like we can task a satellite. Like it's gotten to the point now where there's APIs available where I can literally sit at my desk, draw a polygon on a map, task a satellite, have the image collected within hours and delivered back to me within a few hours. So it's all possible.
That is impressive. Thank you. Another question here, Himadri is asking, is this type of risk analysis mandated by the government? And if so, what are the key advantages of using satellite imagery as opposed to other methods?
It's an excellent question. And in certain jurisdictions, the use of satellite-based ground displacement monitoring has been regulated. I'm specifically thinking of In the United Kingdom, for example, the like one example is a large project was implemented where it's not rail infrastructure, but it's a tunnel where there's a mine, a potash mine that's been developed in one part of the UK, and the potash material has to be transported to a port on the coast. And so that tunneling is going to create ground displacement in and around the surrounding community. And the government of the United Kingdom has mandated the use of satellite-based interferometry to measure the stability of the ground before the project, during the project, and after the project. This would be akin to urban subway development. So if you think about a tunnel boring machine, a TBM, in dense urban areas, the surface expression of the displacement can absolutely be seen from satellite-based INSAR. And so that is another situation where there has been a mandated regulation. I'm thinking of Australia, I think in some jurisdictions in the US and in Canada as well. So it's a great question, and I think it's a good complement to in situ monitoring, because you're getting that regular monitoring over a large area across the entire network. You can go back through time, you can monitor on a regular basis as well.
That is great, Kevin. I want to thank you very much for your presentation today and your candid answers. We have run out of time. I appreciate the extra time that you gave us, and everybody else for staying in the call. I'm sure there's more things to ask you. I see a lot of thumbs up. A lot of people have put in the chat. They're very grateful for you, and it's a very good presentation. So again, thank you. And I have put Kevin's information in the chat. If you have any follow-up questions, you will be able to reach him. You can expect some more information over an email shortly. So thank you, everybody, and have a great rest of your day.
Thank you, Andrea, and thank you everyone for attending. It's a pleasure to be here.
Thank you, everybody. Thank you so much.